we can use the definition of work done to derive the kinetic energy formula. If we look in any situation, work done is force times distance. If we have an object accelerating, then that work done is equal to the kinetic energy. So kinetic energy is force times distance. If we substitute displacement for distance for an object moving in one dimension, distance and the displacement would be the same. And then we can start to substitute for various formulas. So we've got as far as our kinetic energy is force times displacement. We know that force is mass times acceleration. So replacing the F here by ma, we get Ek equals mas. If we then substitute for s using our equations of motion, then we can use the fact that v squared is u squared plus 2as. If u is 0, i.e. it's initial at rest, then v squared is equal to 2as, or rearranging that slightly, a is equal to v squared over 2a. And if we substitute for that, a is v squared over 2s into the formula that we had up here, then replacing that a in there gives us mv squared s over 2s. The s's can cancel out, leaving us the kinetic energy formula. And if u is not equal to 0, then it's worth noting that the work done is the change in kinetic energy, i.e. the kinetic energy before, the difference between it and the kinetic energy afterwards. Notice that kinetic energy of a moving object depends on its mass and the square of its velocity. Now that means you can't, for instance, say the speed changes from 2 meters per second up to 5 meters per second. You can't work out the change in kinetic energy by doing the 5 minus 2. You've got to do the half mv squared for the 5 and the half mv squared for the 2 and take the difference between those two energies. It's also worth stressing that you wouldn't be asked to derive this formula, but it just justifies a wee bit where it comes from.